Hello, welcome back. This is Calculus by Dr. Oz. Today we're starting a brand new topic called applications of differentiation. So we learned lots of rules of differentiation in chapter 3. Now we're going to apply these concepts into applicable problems. And applications vary from offshore drilling to determining speeds of airplanes. And in particular, today we're going to talk about extrema on an interval. And we have three learning objectives to achieve. The first one is understanding the definition of extrema of a function on an interval. And we're going to try understanding the definition of relative extrema of a function on an interval. And eventually we're going to try finding extrema on a closed interval. So let's start with the first learning objective. All right, let's start with the definition of extrema. And extrema is all about finding the minimum or maximum values of functions on intervals. So let's start with the function f defined on an interval containing the point c. And we say that f of c is the minimum of f on the interval I if f of c is less than or equal to any other function value in the same interval. So in other words, f of c is less than or equal to f of x for all x in the interval. And in the meantime, we call f of c to be the maximum of f on I if f of c is greater than or equal to any other function value on the interval I. And in fact, when we say extrema, what we mean by that is the minimum and the maximum of a function on an interval. So these are extreme values of the function on the interval. We're going to also use the terms absolute minimum, absolute maximum, or global min or global maximum for referring to the maximum and minimum of a function on an interval. Okay, and extrema, minimum maximum values can occur at interior points or endpoints. So essentially, if extrema occurs at the endpoints, these are called the endpoint extrema. So in this short video, we're going to try to investigate the extrema of a function on an interval. Here is an immediate comment about extrema of a function. Well, if you start with the function on an interval, that function doesn't need to have extrema on the interval provided to us, or it could have extrema on the interval, but it does not need to have a maximum or minimum. For example, in the first function, you see that the graph has the minimum and maximum happening at x equals 0 and x equals 2, one at an interior point and one at an end point. However, here in the second example, you can see that the minimum occurs at x equals 0 and there is no maximum because here there's a punch and that value 5 will never ever be achieved. So 5 cannot be a maximum value for that reason, and therefore we call that this function does not have a maximum, even though it achieves a minimum value at x equals 0. So far we have had two examples. In the first one, we had a continuous function defined on a closed interval, and we did have a maximum and minimum. In the second example, we started with a continuous function, but the interval was open and we did not have a maximum. I'll show you another example where this time we do not have a continuous function, but the function is defined on a closed interval. Then we do not have a minimum for this function because as you see that at x equals 0, there's a punch here because the function takes the value of 2 instead of 1. Okay, because it's a piecewise defined function, so this breaks the continuity of the function. So the function takes the maximum value at the point x equals 2, but there is no minimum value to be achieved. So for that reason, this function only has a maximum but not a minimum. So now the question becomes, for what kind of functions we do have both maximum and minimum. Is there any bare minimum, or is there any property of a function that we can use to conclude that the function has both maximum and minimum? And the extreme value theorem answers that question. In fact, if you start with the function both continuous and defined on a closed interval a and b, then it's guaranteed for f to have a minimum and a maximum on the given interval, the closed interval. So this theorem is very important because it is sort of like telling us the sufficient conditions for f to have extreme values. Let's go back to the examples and see for which one of them we can apply the extreme value theorem. So in the first example, we had a continuous function on a closed interval. Here we go. We do have the maximum and minimum, so the extreme value theorem is applicable for this type of function. In the second example, we had the continuity, but the interval was not closed. So we're not guaranteed to have a maximum or minimum. In other words, the sufficient conditions of the theorem are not satisfied. And in the last example, we lost continuity even though we had a closed interval. Again, we do not have the sufficient conditions of the theorem. All right, so far we worked on the first learning objective, which is understanding the definition of extrema of a function on an interval. And we also had the extreme value theorem, which provided us sufficient conditions for the existence of extrema. So I think this is the end of the first video. In the next video, I'm going to work on the second learning objective, which is about understanding the definition of relative extrema of a function on an open interval. All right, I'll see you in the next video. Bye.